Hello, everyone. I'm Don Lepp, Editorial Director for the Crane Global Polymer Group. I want to welcome you to this webinar presented by Alpha Technologies and hosted by Rubber News. In this webinar, we will explore the unique capabilities of the RPA through real-world case studies demonstrating how manufacturers have used it to reduce scrap, improve mixing quality, and prevent customer rejections. Today's presenter is Unal Yilmazoglu, sorry about that, Senior Scientist and Global Applications Team Leader for Alpha Technologies. Unal brings over a decade of experience in polymer science. He currently leads the development and implementation of advanced rheological solutions. With deep expertise in polymer characterization, Unal supports global customers in translating complex material behaviors into actionable process improvements. During the course of this webinar, you can ask questions by opening the Q&A icon at the top or bottom of your computer screen and then typing in your question. Your question will be asked in the order received after the presentation portion of the webinar is completed. Let me now turn the presentation over to Unal. Unal, the floor is yours.
Thanks, Tom, for the kind introduction. Today's webinar is all about how the RPA, or the rubber process analyzer, can help you achieve your goals through 10 real-world case studies. So let me begin with the... All right, so here's a quick overview of what we'll cover today. So we'll start with the RPA's capabilities, both for raw elastomers and mixed compounds. Then I will walk you through the instrument itself and how it works. After that, we'll dive into the key viscoelastic data that can reveal production issues and how simply analyzing this data can help solve real problems on the floor. On the right-hand side of the screen, you'll see the list of case studies we'll explore today, from repeatability concerns and extrusion challenges to night shift QC failures and extrusion instability caused by long chain branching. And just for this session, I have added a bonus case study at the end. All right, so when it comes to raw elastomers, the RPA can be a powerful tool for analyzing material stability and identifying potential mixing or processability issues. It provides viscosity data, helps us detect long chain branching, and gives insight into thermal properties. We can also use it to correlate with Mooney viscosity, and once that correlation is established, you may not need a separate Mooney viscometer for routine testing. The RPA can even help evaluate molecular weight and molecular weight distribution variations across different batches. Beyond that, it allows us to determine the linear viscoelastic region, run stress relaxation tests, and detect the presence of gels. With the time temperature superposition, which is TTS, we can broaden the shear rate range significantly, making it possible to simulate high shear processes like extrusion and injection molding. And of course, the RPA is fully capable of performing standard tests according to ASTM, DIN, and ISO protocols. All right, so when it comes to mixed compounds, the RPA can be used to evaluate filler dispersion and determine the degree of silicization. You can run MDR-like isothermal cure tests, as well as non-isothermal tests to simulate real-world temperature profiles and observe how the material responds. It can also be used to perform cure kinetics analysis, monitor blowing or foaming reactions, and check if the material tends to swell during extrusion. Stress relaxation testing is possible as well, along with after-cure property evaluation. And of course, the RPA, again, can be used to perform all the standard tests defined by ASTM, DIN, and ISO. Let's begin with the instrumentation. So on the left-hand side, you'll see an actual image of the RPA testing chamber. On the right, there's a schematic drawing showing the key components inside the chamber, including the torque transducer, temperature sensors, heaters, seals, upper and lower dies, and the direct drive motor. Now, let's take a closer look at each of these components separately. So we'll start with the torque transducer. This component measures the torque generated by the sample as the lower die oscillates. The upper die is stationary and directly connected to the transducer. And the torque values range from 0.02 dnm to 240 dnm, which is why the RPA is considered a high torque rheometer necessary for testing raw elastomers and mixed compounds. Optionally, the RPA can also be equipped with a pressure transducer, which measures the normal force or cavity pressure. This is especially useful for tracking blowing or foaming reactions. With this setup, you can adjust the cylinder pressures up to 90 psi to minimize the slippage and monitor cavity pressures up to 5,000 psi. Next, we have the direct drive motor, which controls the strain amplitudes. The motor covers a wide strain range from plus or minus 0.07% up to plus or minus 1255%, which translates to roughly 0.005 degree to 90 degree. And then the frequency range goes from 0.0016 hertz up to 50 hertz, giving you fine control over test conditions. Then there are highly sensitive temperature sensors and heaters. On top of that, the standard RPA system can operate from ambient temperature up to 230 degrees C. For more demanding applications, there is high temperature option that extends the upper range up to 350 degrees C. We also offer a sub-zero cooling option, which allows testing from minus 25 degrees C to 230 degrees C without using liquid nitrogen. Here we have the dies. The upper die is a stationary plate connected directly to the torque transducer, while the lower die is the moving plate driven by the direct drive motor. These dies are designed with a unique geometry, a biconical or cone and cone shape, which ensures a uniform strain field during testing. And one of the key advantages of the RPA is its closed cavity design. Unlike open cavity rheometers, which can suffer from edge fracture or slippage at high frequencies, the closed cavity helps eliminate those issues and ensures more reliable and reproducible data. There is also an overflow channel, which captures any excess sample to ensure proper sample flash. That flash actually acts as an additional layer of encapsulation, helping maintain the test consistency. Finally, we have seals, which prevent the material from leaking into the hardware components and help reduce friction between the dies and the seal plates. Okay, so let's talk about the operation principle. One of the great things about the RPA is how operator-friendly it is. All you need to do is load the test method into the software, place the bottom film, add your sample, cover it with the top film, and hit start. That's it. The rheometer takes care of the rest automatically. Pretty simple, right? After the platens close, the test begins by applying a sinusoidal deformation, which we call this as a strain. You can think of it like gently pushing and pulling a spring back and forth. In response, the material resists this motion, generating a measurable reaction called torque, similar to the spring pushing back against you. On the right-hand side, you can see something called a phase shift, labeled as delta, between the applied strain and the resulting torque. This is kind of like the lag you feel when you push something really heavy. It doesn't move exactly in sync with your effort. When we take the tangent of this phase angle, we get tangent delta, a key parameter related to processability. Now, it is important to note that the only quantity the RPA directly measures is torque, represented here as S star. This isn't a unique property to the RPA. It is true for all strain-controlled rheometers. Torque is always the primary measured variable. This torque value captures both the influence of the instrument's geometry and the material's response under deformation. From that single torque measurement, we calculate other important parameters, including G star, which is complex modulus, G prime, storage modulus, and G double prime, loss modulus. And these values then allow us to determine tangent delta and eta star, which is the complex viscosity. Let's take a brief look at the viscoelastic data here. So first up is S star complex torque, or G star complex modulus. This represents the total resistance to deformation, a combination of the material's solid-like and liquid-like behavior. You can think of it as how much the material resists being shaped overall. Next, we have S prime, elastic torque, or G prime, storage modulus, which reflects the elastic or solid-like response. It is similar to a spring or a rock. It stores energy and tries to return to its original shape after being deformed. Then there is S double prime, viscous torque, or G double prime, loss modulus, which represent the viscous or liquid-like behavior. Moving on to the eta star, which is complex viscosity, this tells us the total resistance to flow. It gives us a sense of the material's thickness or stickiness under an applied force. And finally, tangent delta, the dampening factor, is the ratio of G double prime to G prime or S double prime to S prime. This is the phase angle, and then the phase lag. It shows the balance between the material's liquid-like and solid-like behavior. A higher tangent delta means the material flows more, while a lower value indicates more elastic and solid-like behavior. Again, it is important to remember that in the RPA, we set the inputs like frequency, strain, temperature, or time, but the only variable directly measured is S star, which is the torque. All the other values, S prime, S double prime, G double prime, G star, eta star, and tangent delta are calculated from that single measurement. Together, these parameters gives us a detailed view of the material's viscoelastic behavior. Okay, so are we ready to jump into the case studies? I can hear yeses. All right. So in this case study, the case study 1, the QC/QA team reported repeatability issues during a string sweep test conducted at 70 degrees C. The data, especially the storage modulus, which is G prime, was inconsistent. To investigate, we looked into the material's thermomechanical stability by time sweep test. It turned out that the original test had been performed without a time sweep or delay step beforehand. These preliminary steps are really essential to ensure both thermal and stress equilibrium before starting any measurement. So we ran a time sweep at 70 degrees C and found that the material reached stability after about 3.5 minutes. This showed us that the material needed at least that much of time to stabilize under test conditions. So to address this issue, we added a 5-minute time sweep test or delay sub test before starting the strain sweep. That simple adjustment or fine-tuning made a significant difference, resulting in much more consistent and repeatable data. In case study 2, a customer reported issues with two polymers that had nearly identical Mooney viscosity values, ml1+4, based on standard Mooney viscometer testing. However, polymer B was showing serious extrusion problems, specifically excessive die swell. They couldn't pinpoint the root cause, and in this case really highlights the importance of using frequent sweeps to more fully characterize raw materials. To pinpoint the issue, our applications team stepped in and ran a frequent sweep using the Premier RPA. And when we plotted G prime versus frequency, we saw that at low frequencies where the Mooney viscometer operates, both polymer A and polymer B looked nearly identical. That's why the Mooney test missed the issue. At mid-range frequencies, some differences started to emerge, but even here, the variation wasn't significant enough to be flagged by an MDR, which typically runs around 1.667 Hz. It wasn't until we reached the higher frequencies, only accessible with the RPA, that the real difference came into focus. Polymer B showed a significantly higher G prime response, indicating greater elasticity. That solid-like behavior is a well-known contributor to die swell during extrusion. And again, this entire test took less than 15 minutes, yet it uncovered a root cause that other methods completely missed. All right, so let's take a look at case study 3. And in this scenario, the customer had two polymer batches that were supposed to be identical. Batch A was produced during the morning shift, while batch B was produced at night. However, batch B failed to meet the quality control specifications. To investigate further, we ran a frequent sweep on both batches, and right away, we noticed a clear difference. when we looked at the crossover points with G prime and G double prime curves intersect, we found that the crossover frequency for batch B produced during the night shift had shifted significantly to the right compared to the batch A. However, the crossover modulus remained roughly the same. This kind of frequency shift typically indicates a lower molecular weight in batch B compared to batch A. Based on the RPA results, we propose a fifth potential causes, such as the temperature fluctuations during polymerization or variations in monomer concentration, both of which can affect molecular weight. Following our recommendation, the customer conducted an internal investigation and confirmed that a temperature spike had occurred during the night shift, which led to increased chain termination and ultimately a lower molecular weight. So in this case, the RPA not only identified the material variation, it also helped guide the theme to the root cause. In case study 4, the customer began experiencing quality issues and a higher scrap rate after switching carbon black suppliers. Interestingly, the new supplier claimed that the filler formulation was identical to the previous one. To identify and troubleshoot the issue, we conducted a strain sweep test. The results revealed a clear difference between batch A, which used the original carbon black, and batch B, which used the material from the new supplier. To qualitatively assess dispersion, we use the pain effect test or strain softening, specifically by calculating delta G prime, which is the difference between G prime at low strain and G prime at high strain. A lower delta G prime generally indicates better filler dispersion. For batch A, delta G prime was 292 kilopascal, suggesting better dispersion. In contrast, batch B showed a much higher delta G prime of 505 kilopascal, indicating poorer dispersion. Since the raw elastomer and mixing conditions were consistent across both batches, this strongly pointed to the filler as the source of the issue. In case study 5, we examine a situation involving two twin plants. Plant A and Plant B, both using the same formulation, raw materials, and processing conditions for a specific compound. However, while Plant B consistently produces material that meets quality standards, Plant A has been experiencing product defects and a rising scrap rate. To investigate the issue, we conducted strain sweep tests again on 3 samples from each plant, and the results revealed a clear difference between the two sets of data. Samples from Plant A showed more pronounced strain softening behavior, also known as the pain effect, beyond the linear viscoelastic region. In contrast, Plant B's data remained more stable. This indicated dispersion issues in Plant A's compound. While we could calculate delta G prime, even a visual comparison of the strain sweep plots made the issue much more clear. The difference in G prime between low and high strain was significantly larger in samples from Plant A, confirming poor filler dispersion. Possible root causes include higher moisture content or inconsistent particle size in the fillers used by Plant A, or suboptimal filler addition sequences during mixing, or equipment-related issues that may be reducing mixing efficiency at Plant A. So this case clearly demonstrates how RPA strain sweep data can reveal subtle yet critical differences in processing performance, even when all variables appear identical on paper. Okay, moving forward to case study 6, the formulation team was working to optimize the final product properties by adjusting the levels of carbon black and oil in the compound. However, the traditional trial and error approach was time consuming. So the question became, can we use the cure curve, isothermal cure curve, to quickly assess the impact of these ingredients? The answer is yes, and this plot clearly illustrates how. The control compound, labeled SPR-NR, includes a typical loading of carbon black, oil, and curing agents. First, when we increased the carbon black content by 10 pHr, we observed a rise in ml, mH, and T90. In another trial, we kept everything else constant and increased the oil content by 10 pHr. Since oil serves as a softening agent, it improves flexibility and processability. As a result, ML, MH, and T90 all decrease. And this case shows how Q-curve data can accelerate formulation decisions and reduce reliance on trial and error testing. All right, so in the case study 7, we are focusing on non-isothermal Q testing, also known as variable temperature analysis, which is VTA. The customer had originally used a different characterization method to determine the optimal Q temperature, which they identified as 185 degrees C. And based on that, they continued conducting Q tests at 185 degrees C. However, at this temperature, curing for 20 minutes led to reversion in MDR cure data, and the final product showed defects. That's when our team stepped in and we applied variable temperature analysis, VTA, using the RPA, where we ramped the temperature from 100 degrees C up to 190 degrees C to observe the compound's thermal behavior in real time. From the results shown on the left-hand side, we identified that 170 degrees C was actually the point where cross-linking reaction initiated. This allowed us to pinpoint a more accurate and effective cure temperature. And follow-up cure test at 170 degrees C for 20 minutes showed no signs of reversion and no issues with marching modulus, indicating a stable and successful cure. So this case highlights how the RPA with non-isothermal testing can be a powerful tool for identifying critical thermal transitions and determining the true optimal cure temperature. This is a really interesting case study involving a customer who had been using a typical MDR, which is moving diameter style isothermal cure test. However, they noticed that the compound's properties weren't aligning with expectations, and they began receiving complaints from their own customers. To investigate, they performed a mold cure and reached out to us for support, asking if we could help simulate their actual mold temperature profile. As we all know, real-world mold temperatures are rarely perfectly isothermal. They fluctuate and they vary throughout the mold. In this case, the customer placed thermocouples inside their molds to record the actual temperature profile during curing. Using that temperature profile, we took the next step with our enterprise database, which allows you to upload a custom temperature profile as a simple text file. With just one click, we were able to run a variable temperature analysis test based on their real mold temperature conditions. By using this actual mold profile, we were able to generate a much more realistic and reliable cure curve, as shown in here. And this approach provided a more accurate picture of the curing process and helped bridge between the gap between the lab testing and in-mold performance. Bringing in real temperature data helped mimic true production conditions, making the RPA data much more relevant and actionable. And here's the quick overview of how you can upload your mold temperature profile into the system. All you need is a simple text file with 2 columns, time in one column and temperature in the other. Using the enterprise database software, just click the import button right here. Once your cure profile is important, simply upload the test method to the RPA and run the test. It's that simple. No complex setup, just real production data-driven, real insights. In this case study, we investigated a quality issue involving anti-vibration compounds made from natural rubber, butyl rubber, and RBR blends. Although the mixes showed no issues in the standard cure data, several final production batches experienced significant product failures and ultimately failed to meet customer expectations. To dig deeper, we performed an aging test using the Premier RPA. And after the standard cure test, each mix underwent a multi-step aging protocol. First, conditioning at 90 degrees C, 1 Hz and 5% strain. Then aging at 30% strain, 15 Hz and a lower temperature for about 1 hour. Finally, returning to the initial condition to evaluate changes in G double prime, which is loss modulus before and after aging. This method is especially useful for antivibration compounds where G double prime is a critical parameter. A higher G double prime value reflects better energy dissipation, which translates to improved vibration dampening performance. Among the 5 mixes tested, mix 1 through mix 5, G double prime proved to be a strong performance indicator. Mix 3 and Mix 5 displayed the highest G double prime values after aging. Notably, Mix 5 also showed minimal change between the unaged and aged G double prime values, indicating strong stability and durability under dynamic conditions, both essential for long-term product performance. And this case clearly demonstrates how RPA aging protocols can uncover subtle but critical differences in compound behavior that standard cure or uncure tests may completely miss. Okay, in our final case study, before we move into the bonus case, we are looking at extrusion instability caused by long chain branching in raw elastomers. In this case, raw elastomers B and C were introduced as low-cost alternatives to elastomer A. However, compounds made with B and C exhibited severe extrusion instability, leading to poor profile formation at the die exit. To investigate the issue, we applied large amplitude oscillatory shear LAOS rheology to assess the presence of long chain branching, LCB, in these EPDM-based elastomers. Using the enterprise software, the long chain branching index was automatically calculated, no manual calculations needed. The results clearly showed that the LCB indices of elastomers B and C were significantly higher than that of elastomer A. To interpret the index, a more negative value indicates a linear polymer, and a positive LCB index indicates the presence of long chain branching, and the higher this index is, the greater the degree of branching. So while elastomer A was confirmed to be linear, elastomers B and C, which were the cost alternatives, showed substantial long chain branching, which helps explain the observed extrusion instability. You can also visually detect branching behavior using the Lissajous figures on the left. So linear materials form simple secondary loop, like the tie shapes here, while branched materials show distorted or more complex shapes. And here are some key takeaways from LAOS study, which is LAOS is highly sensitive to branching, and it allows for quantitative detection of long chain branching. And the LCB index can be a powerful QC parameter for pass-fail criteria in extrusion applications. All right. Now, I'd like to take you on a different journey on that we call precision dynamic modulus, or PDM. PDM is a new capability made possible by the next generation RPA platform, which is RPA Plus. This upgraded system includes a die gap sensor. Sorry about that. Includes a die gap sensor, smart pressure regulator, and premier seal plates. But the real innovation lies in the die gap sensor, a technology first introduced by Alpha Technologies and currently the only commercial rheometer on the commercial RPA on the market capable of measuring sample thickness in real time during testing. Here's why this matters. As a background, moduli G star, G prime, and G double prime are calculated by multiplying the measured torque, which is the only direct output of an RPA, by a geometry-dependent constant, which is C, and then dividing by strain, gamma. However, that constant, which is C, is directly affected by the sample thickness. Most commercial RPAs assume that sample thickness remains constant throughout testing, but in reality, that's not in the case, because especially during the testing, where shrinkage or expansion of the sample can significantly affect its thickness. This is where the die gap sensor becomes essential. By measuring the actual sample thickness during the testing, PDM technology accounts for changes that will otherwise skew your results. And in our studies, we observed that PDM can reduce variation by as much as 50%. For example, in an after-cure SPR compound test, we compared the standard method, which is the standard commercial RPAs, with the PDM-enabled approach, which is RPA plus, and the result, a 50% reduction in the coefficient of variation, just by incorporating real-time thickness correction. So in summary, PDM improves test reliability, enhances data accuracy, and brings a higher level of confidence when comparing materials that are prone to expansion, shrinkage, or batch variability. Okay, so now that we have covered the PDM technology available with RPA Plus, our next generation instrument, so let's wrap up with a bonus case study focused on shrinkage detection. So in this case, a compound passed all standard MDR tests without issue. Cure data looked normal. No significant differences in ML, MH, T10, T50, and T90 values. However, once the material was processed into final parts, it exhibited unexpected shrinkage and dimensional inconsistencies during production. To investigate this issue, we ran a standard isothermal cure test using the RPA Plus. As expected, it mirrored the MDR results, no significant differences in conventional cure parameters. However, what makes the RPA Plus unique is its dye gap sensor, which continuously tracks sample thickness during testing on the right-hand side. So during the cure process, you typically expect a reduction in thickness as cross-linking occurs. And in this case, the dye gap data didn't show any major difference between samples during curing. So we moved on to a temperature sweep test, starting from 170 degrees C and cooling down to about 70 degrees C. So this is where the difference became much more clear. Compound B showed an 11% reduction in sample thickness as it cooled. On the other hand, compound A showed a 40% reduction, a clear indicator of shrinkage behavior that wasn't captured in the isothermal cure test. What is important here is that the dye gap sensor tracks thickness in real time, and those values are automatically integrated into the calculations of G prime, G double prime, and complex viscosity, giving you more accurate and more precise rheological data. At the same time, the thickness data itself becomes a direct diagnostic tool to assess shrinkage or expansion during processing, something not possible with traditional rheometers. This case basically perfectly illustrates how PDM technology and the dye gap sensor provide deeper insight into compound behavior, detecting real-world processing issues that will otherwise go unnoticed in standard cure testing. Thank you very much for your attention. Now, I think it's time to move into our QA session. On the right-hand side of your screen, you'll see a QR that links to our Relaxation Times blog. From there, you can access application notes and other valuable resources related to RPA and the broader range of instruments available from Alpha Technologies. Thanks again, and I'll look forward to answering your questions.
Thank you, Yunal, for a great presentation outlining the capabilities of RPA. We're now ready for questions. As a reminder, you can click on the Q&A icon at the top or bottom of your computer screen and type in your question. Your questions will be answered in the order received. We'll start with a couple that came in during the program just because a few people asked about we'll be sharing this presentation, and the recording will be on rubbernews.com within 24 hours, and the presentation itself can be provided upon request, and you'll see the contact information for Yunal there. So you can, if you want a copy of the presentation, make sure to get his contact information and request it there. So some questions that came in prior to the event today. First one, relying on just one supplier of raw material, especially a polymer supplier, is risky. And also, we don't have bargaining power for their cost. So we are trying to approve a new ESBR OE, or oil extended supplier. But after we apply inside the CB tread compound, the MV compound becoming higher than control, and then alter extruding the surface of slab tread, becoming rough, not smooth, slab tread profile, becoming over than standard. Can RPA detect from the raw material polymer properties, which can create such kind of issue above. So another,
I think this is a
yeah,
really great and then a very well
yeah.
articulated question. And then
Mhm.
the answer is definitely yes, especially the final case studies that I showed, the long chain branching may affect these properties. So you could root cause with an RPA, with a Premier RPA effectively.
Okay, and another question. Now the SSBR product and supplier are many in the market. There are many developments in the chain with some functionalized that can capture more bonding with silica or other filler. How can RPA help us to check whether the SSBR is easy to process in the Banbury or not?
Again, great question. For the processability, especially for mixing, I haven't showed in this case study webinar, but there's an option that you could run a strain sweep test. And then by just not looking at the G prime versus strain data, you should look at S prime versus strain data. And if you see there are some inconsistencies like sharp peaks and then the abrupt changes in the data, it gives you an understanding of whether this material is feasible to process or you should make some modifications. On top of that, with the end functionalization, you could also identify these differences with loss testing.
Okay, very good. This question came in while you were presenting the number 7 case study. And the question is regarding number 7. Normally, what may be the temperature rising rate for NR-based compound?
Good question. So for the especially when it comes to natural rubber, there is a lot of heat history sometimes happening in the natural rubber. So what I will do is I will condition at 50 degrees C for a couple of minutes, like 4 minutes, 5 minutes, and then ramp it with 5 degrees C per minute slowly to raise that thermal history and go up to around 150 degrees C to get more effective the cure temperature determination.
Okay, a lot of questions coming in. We'll get to all of these, I think. Next one, thanks for your presentation. What deformation and temperature did you perform the crossover point to increase this elastic window when creating a master curve? What temperature jumps should be made? I'm referring to the time temperature superposition. Thank you.
Perfect question. So in the crossover point determination, I use 7% strain at 100 degrees C. And then, especially when it comes to TTS, I will suggest at least the temperature window should be plus or minus 10 degrees C. And then I will run perhaps 5 different temperatures to get a much more reliable master curve. But for the follow-up information, I would say that when you perform the TTS curves, people sometimes often miss that the TTS is not always applicable to the raw elastomer. So that's why I will always go back and run some Laos tests to determine if the material is branched or linear. And after I confirm the material is linear, I will perform the TTS testing with plus or minus 10 degrees C increments.
Okay, sounds good. Next question. Someone's asking for some help with a couple of methods and analysis. The first seems to be a compound shelf life for both extension and analysis of water absorption. And this is for silicone-based compounds. I'm going to cover that one first.
Yeah, for the compound shelf life, I think this question addresses for the aging case study that I showed lately that you could perform an aging study to assess the shelf life. And for extension, basically RP is a shear rheometer. It does not operate in an extension wise, but in the past papers that we proved that there's a linear correlation with the correlation of coefficient of R square 0.99 with the tensile testing. So as long as you create that correlation chart, you don't need to run extension tests anymore. But again, the RPA is just a shear rheometer, it's not an extension rheometer. And for the water absorption, it's going to be a little bit more tricky in this case because RPA is a closed cavity. So It's a pressurized cavity also, and then it's really hard to make it environmentalize while testing. So if you come up with a basically really niche method to assess the water absorbed silica filled compound and not water absorbed, you can see the differences, but not in the testing chamber.
Okay, and their second question, green strength measurement for the stripped compound that is to be fed into an injection molding machine.
Yes, I think the question is, can we do the green strength
Yes,
measurement? So
that's right.
not again directly with the RPA, because the RPA uses oscillation to identify the viscoelastic properties. But again, in the past, we also proved that the green strength, we correlated the RPA data with the green strength, and we again achieved a really good correlation. So I mean, if you're interested, please send me an email. I can send you that paper.
Okay, and then their last question specific was referring back to case study number 3 using RPA, how reliable would a quantitative analysis of MW or MWD be? And what about after curing? Could you determine the MW of uncured chains?
Good question. So for row elastomers, actually, when it comes to crossover point, you're not going to see any crossover point in field compounds. If your filler loading is like 0.05 pHr, you will definitely see a separation. You're not going to see any molecular weight, and you're not going to see any crossover point change. But by just looking at the G prime data, if you experience much higher G prime response, this is an indicator of the high molecular weight. And if you're asking for modeling, so modeling has some caveats. For example, again, this modeling does not work very well for the field compounds. I'm talking about not the data analysis, this actual modeling. So this quantitative description sometimes misleads user. So I will for the QC analysis or any R&D purposes, I would have a material which is known molecular weight and molecular weight distribution, and then I would compare by looking at the RPA data qualitatively, or by just looking for G prime, G double prime responses.
Okay, very good. Next question is a manual available to help us interpret these measurements.
Yes. So in our website, we just recently launched a customer resource hub. If you have a Premier RPA user, so you basically submit a ticket, and then whenever you're approved by the system, and then there's knowledge articles in there, and then we also launched Rheology 101 and RPA 101, which the similar course that I presented today. And then you can access these resources with our website.
Okay, lots of questions. Keep them coming. Is it possible to correlate MDR or Mooney with RPA?
I will say MDR is the grandfather of the RPA. So in MDR, basically you are using an isothermal cure, the only capability of an MDR. So yeah, you don't need to do any correlation. You can basically run exactly the same test with an RPA. And with the RPA, yes, question is yes, you can have a really good RPA Mooney correlation, ML1 plus 4, ML1 plus 8, and etc.
Okay, good. Next question. How can we get the test condition for each case from ASTM standard or I guess somewhere else?
If you could send me an email, that would be great, because in some case studies, it's not a traditional testing conditions. ASTM, ISO, and DINs are really great guidelines. But in some cases, I used basically the different test conditions than these standards. So if you could shoot me an email, I can basically enlighten you which test conditions that I use.
Okay, another specific question about one of the case studies. In case number 9, why did you use 30% strain for aging? Is there any slippage of the sample inside the rheometer?
Great question. So there are actually two things why we picked 30% strain, because when you go to higher frequencies, like I used 15 hertz, if you go beyond 30% or 40% strain, you start to see slippage. So that's why we limited at 30%. And then this slippage can be easily detected after 40% strain. So at 30% strain with 15 hertz, there is no slippage signs that we have detected from the material.
Okay, next question. I think this came up while you were talking about the training. Do you provide a training certificate?
For the webinar, we haven't discussed this yet, but for the trainings that we are giving to our customers or in some trade shows, we are basically giving that training certificates, but not necessarily for webinars.
Okay. Does RPA can be adjusted die height, for example, to have similar results to MDR rheometer?
Yes, the case study is up to 11. The last case study we use the default Premier RPA, which the die gap is around, which the die gap is around 0.4776 millimeter. And then this is the standard for MDR2. You don't need to make any adjustments for the standard RPAs.
Okay, good answers. Next, is there any possibility to understand the normal SSBR and functionalized SSBR?
Yes, with the Laos test, you will see the Lissajous figure have distinct properties, distinct signs that show you whether your end functionalization might be pom-pom, star shape, and etc.
Okay, good. Next one. Can you explain the kinetic parameters that can be obtained in RPA?
Great question. So with the RPA, from the Q kinetics, you could get the Arrhenius type activation energy, and then the reaction orders of the material. And then the benefit of using the RPA in our software is when you run at least 3 Q tests with different temperature, let's say 160, 170, and 180, all you need to do is just use a Q kinetics button, and then it calculates automatically. And it shows you the reaction orders, activation energy, and etc.
Okay, good. Next question. Could you comment on the sub-ambient test capability and how you compensate for thermal contraction and expansion?
Excellent question. So for the subambient temperature testing, which I mentioned from -25 to up to 230 degrees C, it comes with an RPA plus. And then if you remember with the RPA plus technology, which is the PDM technology, this measures the axial sample thickness. And it gives an understanding. It provides you a correction in G prime and G double prime values. So you are basically getting much more accurate values.
Okay, good. Next question. Does your RPA have a test to give insight on how thick cross sections will cure versus the RPA thin disk result?
Um, I'm not sure I understood the question properly, but let me articulate it. So if the question is, can we correlate the actual cross sections, shrinkage or etc. with the actual the die gap sensor result, because RPA and MDR test typically uses the slabs that you cut and then place it there. And yes, there is a correlation that you could have an understanding of what could be the production at the end of the production thickness.
Okay. Next question. Is it possible to have a step or preheating with no movement, to have preheat without mixing, degrading the compound for a very soft compound?
It is possible, yes. If you set the strain and frequencies to 0 at the beginning of the test, and then after you condition the test or the temperatures and then or the conditions that you prefer, and then all you need to do is just a little bit of the additional test shows you the recovery of your material, and yes, it's possible.
Okay. Is it possible to have a graph or a customized background to have, for example, a golden or reference batch with limits for production operators to easily see if production is standard?
It is have. So we have a statistics package in the enterprise. So you can basically pinpoint and then identify, hey, this is my golden batch, and then you can check the how it varies in terms of statistically. You can check plus minus 3 sigma and the other statistical coefficient of variations, etc. Yeah, it's with the statistics package, you can easily achieve this goal.
Okay. Next question. Generally, for extrusion performance, I look at complex viscosity at different strains and temperatures from the RPA for a basic picture of the material's resistance to flow. What other parameters might be useful to pay attention to as it relates to extrusion? I know you mentioned die swell and LCB.
Great question. So especially I will look at the gels, if that's the case in your material. And then I'll look at the tangent delta frequency graph, even if it's a compound, and then to check if there's a gel presence. The gels show itself basically with the flat tangent delta response, and then it could give you an understanding of extrusion problems apart from the frequency sweep test and the loss test.
Okay, question here. Technically specified rubber from different suppliers. Can it be this? Can it be the same? Can an RPA be able to detect the differences? So differences between specified rubber from different suppliers.
If there are differences, yes. If there are differences, RPA can effectively show you if these two materials are different or not.
Right. Okay. What's the lowest temperature that your RPA can test cured samples to determine, looks like tan deltas?
Yeah, tangent deltas. Yeah.
Tangent, right.
Yeah. So with the Premier RPA, the lowest end is like ambient temperature. So if you have an RPA plus, so you can go down to minus 25 degrees C. And then the question was, I believe, the highest strain was, right? Yeah.
I think it was the lowest temperature.
Lowest temperature, yeah, the lowest temperature. Basically, if you have a sub-zero option, you can run a strain sweep test or frequency sweep test at minus 25 degrees C, and then you can again, if you have a traditional Premier RPA, you can go down to ambient temperature to check your tangent deltas.
Okay, good. Next question regarding RPA slippage. What's the highest durometer you can test successfully, and how is slipping determined?
Good question. The slippage is technically determining by so this is a really tricky question. The first thing first is it comes with an experience. I'm not gonna say that. I mean, it needs a really deep knowledge of the experience. But for example, if you're on a frequency sweep data, and if you go really high frequencies, and if you see a decrease, the oscillation-wise decrease in the G prime or G double prime curve, which is supposed to be in increase fashion with the frequency, you understand that this is a sign of slippage. And you can also check the tangent delta, which, let's say you test two materials and one gives you a lower tangent delta, but with the higher test conditions, higher strain and frequency, if you are getting much more higher tangent delta, this is an indication of the slippage.
Okay, good. Hey, thanks everybody for hanging on with us. We've got quite a few people still on the line, which is terrific. Next question, is there a source where I can download ASTM methods or recommend methods from your studies?
To download ASTM methods, you should subscribe to ASTM, so it's not downloadable. And for our case studies, if you could check our customer resource hub, if you have a Premier RPA or RPA 2000, you could see that I am step by step showing you how to create this test and explaining the conditions.
Okay. Next question, which parameter is key for predicting a pre-vulcanization in a method that simulates an extrusion and a subsequent remill of a rubber?
Oh, that's a hard one. So for the pre-vulcanization, or if we are talking about scorch, I will look at the G prime or S prime response, and then I will definitely use variable temperature analysis, not the traditional isothermal cure test, because it doesn't sometimes show you if there's a premature curing or etc. And then you will see when you run the VTA test, you will see that while you're ramping up, there's a little bit of bump occurs, and then it shows you the pre-vulcanization.
Okay, good. Next question. Have you ever seen a case where Mooney, viscosity, and RPA data told conflicting stories, and how did you resolve it?
Oh, this is actually the case study, I believe the case study second, or let me go back and show it to you really quick. So, and this case studies are perfect for this question because if we look at in this case study, the Mooney values are typically the same. So you cannot distinguish with a Mooney. And then when you go up to higher frequencies with the RPA testing, you can understand which one has a higher G prime, which is more or less directly linked to the extrusion problems.
Okay, good. Next question. Have you encountered compounds that show good cure curves but fail performance expectations? And if you have, how did RPA help resolve that?
The good question is, again, for the Q curve, if you remember the last case study, I'm gonna go over there. Especially, let's take an example of the shrinkage that we've seen that the Q curves are okay, so it didn't show us any problems over there. And then it definitely passes the QC/QA specifications. But if you check with the RPA Plus and then look at the sample thickness change, you'll definitely identify material B and A are different, and then A has much more shrinkage compared to A.
Okay, looks like we've got time for just a couple more questions. Next one, are there any automation options available within the RPA?
There are automation options. So we have 5Q, 10Q, 64Q, if I'm not mistaken, and then it goes up to 200-ish Q. So it's fully automated. As long as you cut your samples, you place it to the automation queue, and then hit the button. So when you come back in the weekend, you'll see that all your tests are completed.
Oh, okay, very good. Another question, is the RPA or its software capable of performing any statistical analysis?
Yes, the statistics package that we have shows you the descriptive statistics, giving you plus or minus 3 sigma, and it can help you to guide to set your specs. And you can take detailed reports with just one click.
Okay. This last one looks like it's more of a comment, but we will ask and maybe you'll have a comment back. Says, congratulations on the presentation. These cases are very real and common, and it was clear how RPA can easily assist in solving these problems. I was particularly impressed by case number 8, which demonstrated the versatility of both the equipment and the enterprise system. Also, it's really interesting to learn more about the PMD technology because, yes, the thickness of the sample is very important, and this is something difficult to have control over. Any comments on that comment?
Well, thank you very much for the really kind comment. Yes. So with the enterprise, it's in some cases looks a little bit complex, but it gives you a much more flexibility that you can run statistics, Q kinetics. It's a great database and software for the production floor, and there are some features which are basically looks hidden, but I wanted to point it out. So there's an option that you could upload your temperature profile easily with just one click, and then also the PDM sensor technology can give you the real-time thickness measurements during testing, which improves your data accuracy and repeatability.
Okay, if if you'd like to scroll back through your presentation back to the last slide so we can show folks the contact information, very good. So thank you very much for attending this Rubber News webinar presented by Alpha Technologies. We appreciate all of your great questions, and I want to thank especially Ünal Yilmazoglu of Alpha Technologies for a great presentation and for answering all of the questions that you had. If you have any further questions or want to reach out to Ünal directly, contact information is on your screen. Finally, you will find today's presentation by going to the webinar section of the Rubber News website. The presentation will be posted within 24 hours of today's webinar. Thank you very much for attending, and we'll see you at a future webinar.
Thank you, Dan. Thanks for your attendance.